This is what I think is the actual stellar evolution timeline, okay? What happens is you have a newborn star, and those are the nebulas, the planetary nebulas that are really, violent looking. They have these weird rings around them, and that's evidence for magnetic fields being in there. It's evidence for a lot of activity. And you'll see them doing really strange things, and then you'll see a little dot in the center. And I think that dot in the center is the very brand new star. And as it's being born, it then sheds away all of its material away, and then boom, the umbilical cord, if you will, is released, and the star is a white dwarf. And that's a newborn star. They're about 1 million years old. And what happens is the star expands as it's trying to radiate the heat away, and it expands even more, 5 to 10 million years old, and expands even more. And then it reaches a point to where it gets the biggest it can get, and that's about 10 to 20 million years into the star's lifespan. Then you have the smaller blue stars. They're still very, very hot. And then you get the white spectrum stars, and then the yellow spectrum stars, which is the sun, and the sun is around 60 to 100 million years old. And then you have your orange dwarfs, and then you have your red dwarfs, and you have your auburn dwarfs. That's what I call them. Then you have Jupiter and Saturn. You have your gray dwarfs, and then you have your Neptune and Uranus worlds, and then you have ocean planets in between Neptune and Uranus and Earth. And then you keep on cooling, and dying, and eventually the star dies completely, and it becomes something like Mercury or Venus. And they just populate the galaxy all over the place, and then just smash into whatever it is that's in their way. To me, it makes more sense to have the star start out as something that's very turbulent and violent and electromagnetically powered, and then it retains its spherical shape as it moves along basic evolutionary paths.